Welcome to Homework Lib.
Hi, so over here to prove that an ideal gas is going to be depending only on the temperature of the gas and its internal energy, we know that the enthalpy for a definition is going to be equal to U plus PV. In the case of an ideal gas, nRT is equal to PV, so the enthalpy is going to be U plus nRT. Thus, we can calculate the change of enthalpy as change of internal energy plus nR times the change of temperature, only for an ideal gas. So, as you can see, any change of enthalpy is going to depend only on the change of temperature and the change of internal energy of the gas itself. Now, we know that for an ideal gas, the change of internal energy is equal to N times Cv delta T for a process at constant volume. So, whenever we have a process for the part A, in which an ideal gas goes from T1, P1 to T2, P2, if we calculate the change of enthalpy, we're going to find that this is going to be equal to NCB times delta T plus NR delta T. As you can see, there is no dependence on pressure. Now, whenever we take a process in which the ideal gas only changes from temperature 1 into temperature 2, the change of enthalpy is going to be the same, NCB delta T plus NR delta T. Finally, for this problem, we're told that we need to calculate the change of enthalpy for 2.5 mole of an ideal gas that has a change of temperature of 50 degrees Celsius, which is positive. Remember that 50 degrees Celsius, whenever we have a change of temperature, is the same as 50 Kelvin because the conversion from Celsius to Kelvin is linear. You don't need to add any other factors. And finally, we're told that the change of internal energy, there is a typo in your question, it states delta H, it should be delta U, is equal to 3,500 calories per mole. The value for the gas constant R is equal to 1.98 calories per mole Kelvin. 1.98 calories per mole Kelvin. So whenever we want to compute the change of entropy, we said that it was equal to delta U plus NR delta T. This becomes 3,500 calories per mole plus 2.5 mole multiplied by R, which is 1.98 calories per mole Kelvin, multiplied by delta T, which is 50 Kelvin. Mole and mole cancel out, Kelvin and Kelvin cancel out, and the change of internal energy we need to multiply by the number of mole as well to have the value for the whole process, not as a molar quantity. So the result of this change of enthalpy is equal to 8,997.5 calories per mole. Sorry, calories alone in this case, since we already got rid of the mole quantities, which is approximately 9 kilocalories. So that would be all. Thank you very much and have a good one.